All right, the next video in our stoichiometry unit is going to focus on bits of empirical molecular formulas as well as mole conversions, and that's going to involve combustion analysis. And basically what's happening with combustion analysis is a compound is undergoing a combustion reaction, and as that occurs, samples of amounts of the gas are collected, and we are able to use those amounts to determine what the composition was of the compound we started with. So this is just an example combustion equation. It does not have to necessarily just consist of carbons and hydrogens and possibly oxygen. It could just be a hydrocarbon with carbons and hydrogens. Or there could be sulfur present, there could be phosphorus, it could be another compound that's undergoing combustion. But generally speaking, the ones we're going to be dealing with are going to be organic in nature. And so you see the general equation there where you have the hydrocarbon combining with oxygen to produce two oxides, one involving carbon and one involving hydrogen. If we know the amounts of the products, if we know how much CO2 we were able to produce, we can work backwards using the relationship between carbon dioxide and carbon to determine how many grams of carbon were initially present. If we look, there's only one source of carbon on the reactant side, and there's one product that contains carbon. So that's why we're able to do this. It's not being found in multiple reactants or multiple products. We also can do that with hydrogen, specifically with water. But we need to keep in mind with water that there are two hydrogens present in water. So when we go backwards, we need to account for the total number of hydrogen that were present in water initially. If you happen to have a third element present, if you know the mass of the compound that you started with, and you know the amounts of or all the other elements besides the one you're looking for, we can use conservation of mass to determine that remaining element. And at this point, once you have done these conversions, this goes back to being an empirical formula problem. So here we have just a hydrocarbon, which means it just contains carbon and hydrogen, and we have the amounts of CO2 and the amounts of H2O that are made. So we're going to figure out what the empirical formula is of this compound, and then knowing what the molar mass is of the hydrocarbon, we're going to determine its molecular formula as well. But first things first, to determine the empirical formula, we need to know the masses of the elements that made up our compound. So we need to know how much carbon and how much hydrogen we initially had. So if we started with 2.703 grams of carbon dioxide, we know what the relationship is between carbon dioxide and carbon in this compound. That the molar mass of carbon dioxide is 44.01, 1 C and 2 O's. And because there's only one carbon in CO2, the mass of carbon would be 12.01 towards that 44.01 grams. The grams of CO2 cancel out, and when I multiply and divide, I get that 0.7376 grams of that compound, the 2.703 grams of CO2, was made of carbon. Again, we're assuming everything went perfectly. That's the only way you can really do problems like this. If I wanted to know about the hydrogen, I would use my 1.108 grams of water, and I would work backwards from water to hydrogen. Keep in mind with hydrogen, because there are two hydrogens making up H2O, you would need to account for both hydrogens or have 2.02 hydrogens for every 18.02 grams of water. When I do my math through, after canceling out my units, I need to have, probably should have had 3 sig figs. I went ahead and kept 4. It's fine. 0.1242 grams of hydrogen. So I have masses of the two elements that were making up my compound. And if I want to find an empirical formula, that's my starting point. That's step one, is get my grams. And then I want to convert them to moles using their molar masses. And that gave me 0.06142 moles of carbon and 0.1230 moles of hydrogen. I divide by the simplest number of moles, or the smallest number of moles, so I divide by the carbon moles, and that gives me a ratio of roughly 1 carbon for every 2 hydrogens. So that would be the empirical formula for this particular hydrocarbon. The molar mass of that empirical formula would be 14.03, 1 carbon plus 2 hydrogens. My actual hydrocarbon had a molar mass of 56 grams per mole. So if I take that molar mass and divide it by 14.03, I get that the empirical formula is going to be 4 times simpler than the molecular formula. So if I take my CH2 and I multiply each of my subscripts by 4, I get that my actual molecular formula is C4H8. So that was one example where you had just the 2 elements and you could work backwards from carbon dioxide and water. In this one, we have a third element, we have oxygen. You can't use the oxygen in CO2 and the oxygen in water to determine how much oxygen was present in your initial compound, because remember, with the combustion reaction, O2 is also a reactant. So we're going to have to use the CO2 to get our carbon, and we're going to have to use the water to get our hydrogen. And because we know how much of the compound we had present, we should be able to use conservation of mass to determine what fraction of that compound was actually oxygen. So I'm going to take my grams of CO2, just like I did in the previous example, and determine what part of that compound by mass is carbon, using the molar masses of carbon and CO2 respectively. And I get that 11.46 grams of that compound came from carbon. If I use water and find out the grams of hydrogen from water, again, accounting for the 2 hydrogens present in H2O, I get that 0.723 grams of this compound was hydrogen. Now, I know the mass of my total compound is 19.81 grams, and I know the part that's carbon, and I know the part that's hydrogen. So if I substitute in what I know, I should be able to algebraically solve for what I don't know, which is oxygen. 7.63 grams. I now have the grams of the 3 elements that were present in my compound, part 1 of my empirical formula, and I can use those grams to get moles using the molar mass of those 3 elements respectively. The grams cancel out, and that gives me moles of carbon, moles of hydrogen, and moles of oxygen. I'm sorry, the C in the last one's a little bit cut off. I think it is on your slide anyway. I'm sorry. Now that I have my moles of my respective elements, I take the one that I have the fewest of, which would be oxygen, and I divide all of my moles by that one. I get that carbon has a ratio roughly of 2, hydrogen has a ratio roughly of 1.5, and oxygen has a ratio of 1. Again, I can't just round up halves, so if I have to double the hydrogen, I also have to double the carbon and the oxygen. And by doubling it, I get 4 carbons, 3 hydrogens, and 2 oxygens, making up the empirical formula for this compound.